Hello students! So this is the second in the sequence of videos introducing you to limits and continuity of functions. So something that's relevant to point out is the definition of the limit of a function looks very much like the definition of the limit of a sequence, and maybe it's worth recalling each of those. So we say that limit as x approaches p of f of x is equal to L. That means for all epsilon greater than 0, there exists a delta greater than 0, such that for all x in U, if 0 is less than the absolute value of x minus p is less than delta, then absolute value of f of x minus L is less than epsilon. On the other hand, the definition of limit as n goes to infinity of a sub n is equal to L. That means for all epsilon bigger than 0, so verbatim the same, there exists a big N, not totally dissimilar, such that for all n in N, that's a fairly reasonable analogy. This U is the domain of the function. The set of natural numbers is the domain of a sequence. If little n is bigger than big N, then absolute value of a sub n minus L is less than epsilon. So again, there we see basically the exact same thing. And these two kind of correspond too. Little n is bigger than big N is somehow saying that little n is somehow close to infinity. Whereas this is literally saying x is close to p. So the two ideas are so very similar, it's not surprising that they should have similar properties. So let's just state them. If you take a constant function, okay, so let's set all the setup. So let's let U be a subset of R, P be a limit point of U. You have to be at a limit point to take a limit. And F and G be functions defined on U. If f of x is equal to c is a constant function, then limit as x approaches c of f of x is c. If f of x is equal to x is the identity function, then the limit as x approaches p of f of x is p. If the limit of as x approaches p of f of x is equal to L, and the limit of g of x is equal to m, then the limit of the sum is just the sum of the limits. L plus m. The same thing is true for subtraction. The same thing is true for multiplication. The same thing is true for division, with some caveats. Namely, you need to make sure you never divide by 0. So g of x better never be 0. M had better never be 0. As an immediate consequence of these, we get results for continuity. The function given by f of x equal to c is continuous on the whole of the real line. The function given by the identity is continuous on the whole real line. If U is a subset of R, P is in U, and F is continuous at P, then a number times F is continuous. If you take two functions and add them together, if both of those functions are continuous at P, then the sum is continuous at P. If two functions are continuous at P, then their difference is continuous at P. If two functions are continuous at P, then their product is continuous at P. If two functions are continuous at P, and g of x is not equal to 0 for all x in the domain, then the quotient is continuous at P. And this is labeled as a corollary of that theorem. I won't prove that theorem. Maybe I'll say this about the theorem. Proofs are same as proofs for sequences. Right. Take the proof of the corresponding claim about sequences, port it over, and you'll get a new proof. If you like, I have uploaded a proof of this item, which you should take a moment and look through. I'll also, in the next lecture, prove these from the by using a philosophy about continuity and limits that comes from limits of sequences. So we will actually prove them, but for now, the proofs are the same as the proofs for sequences. So let's prove these. They all, in fact, have the same proof. So I'll go ahead and jump right down to claim 7, which is the most complicated of them. So if I can do that proof, you should believe me that all of them will follow easily enough. So let's suppose that U is a subset of R, P is in U, and F and G are functions from U to R. Oh, maybe you noticed that here I say that we'll do claim 7 together. I guess we can't do it together if I'm doing it in advance. But in fact, you should pause, fill out this, and then see if you agree with what I write. So we want to show that F over G is continuous. So I know things about limits, and I know limits have something to do with continuity. Namely, I know two things. This is off to the side. This is from the previous lecture also. I know that if P is in U and P is a limit point of U, then F, a function, well, F is, whatever, is continuous at P if and only if limit as x approaches P of f of x is equal to f of P. I know that if P is isolated in U, so if P is an isolated point of U, then no matter what, F is continuous at P. And those are both things that we did last time, as in the previous video. So let's use those two cases. So I'm interested in F divided by G. So if P is an isolated point, then by proposition 3.16, that's that claim. Any function is continuous at P. I care about F over G is continuous at P, as we needed. If P is a limit point, then I can translate from continuity to things about limits. Since if P is a limit point of U, then since F and G are continuous at P, then I can apply theorem 3.1.5. to see that f of P is equal to the limit f of P is equal to the limit as x approaches P of f of x, and G of P is equal to the limit as x approaches P of G of x. So I can use theorem 3.17 claim 6. Let's go ahead and scroll up and remind ourselves that, which says that if f of x converges to L and G of x converges to M, and G of x is not equal to 0 forever, and M is not equal to 0, then the limit of f of x over G of x is the limit of f of x divided by the limit of G of x. Well, let's see if I have all of that. Limit of f of x is a thing that exists. Limit of G of x is a thing that exists. G of x is never equal to 0. The limit of G of x is also not equal to 0. So that's everything I need to appeal to the theorem. So by theorem 3.17 claim 6, we have that the limit as x approaches P we have that, sorry, maybe I'll figure out how to zoom correctly. Limit as x approaches P of f of x divided by G of x is equal to the limit of f of x divided by G of x, so that I can again appeal to theorem 3.1.5. I have the limit as x approaches P of a function, namely this function, is equal to that function evaluated at P. So I can conclude that f divided by g is continuous at p. So the idea here is, if you know that limits are somehow equivalent to continuity, then every fact you know about limits is a fact about continuity. And here's one which you should do on your own, certainly, before I talk through it. I will talk through it right now. But you should pause right now and complete the proof of claim 6. So let's go through it together now. So let's suppose that U is a subset of R, P is an element of U, and F and G are continuous at P. I need to show that F times G is continuous at P. Well, first, if P is an isolated point, everything is continuous at an isolated point. Then F times G is continuous at P. There's nothing to prove. If P is a limit point, then since F and G are both continuous, I know that the limit as x approaches P of f of x is equal to f of P, and the limit as x approaches P of g of x is equal to g of P. Because continuity if and only if limit is given by plugging in. So by theorem 3.17 claims 6, which hopefully is the one that involves multiplication, I can conclude that the limit as x approaches P, maybe I'll write down more details on this one, f of x times g of x is equal to the limit as x approaches P of f of x multiplied by the limit as x approaches P of g of x. But I know what those two things are. That's f of P times g of P. So this shows that the limit of f of x divided by g of x is the same as plugging P into f of x times g of x. So I can appeal to theorem 3.1.5 to see that f multiplied by g is continuous at P. Completing the proof. And this is, I know, a really short video, but that's where I'll stop.